Welcome back to ECE 501B. Just as way of announcements, remember homework 7 and 8 are still due. One is due on the 23rd of November and the other one is due on the 7th of December. Your project is due on the 9th of December, and the final exam is on a Tuesday, not a Monday or a Wednesday, but it's on Tuesday, the 15th of December from 6 p.m. to 8 p.m. It's a 2-hour final. What I want to do today is recap what we mean by a positive operator. And when you think of or hear positive operator, you might think scaling. Think of that like a positive number. It can either contract or expand in terms of be bigger or less than 1. And then we will go ahead and rewrite or state Theorem 727, which deals with this equivalence of conditions or statements concerning positive matrices. Then we'll look at some examples of positive matrices and maybe even remind ourselves of some of the square roots that we talked about last time or demonstrated last time. Then we will go back and prove Theorem 27. We will state Theorem 728, which talks about every positive operator having a unique positive square root. And then we will get into this second sort of part of an operator that we will introduce, which is isometries. And with an isometry, now you think rotation or direction versus with the positive operator you were thinking scaling. So now let's look at or remind ourselves what we have started to look at, and that is these positive operators. It's made up of two pieces. One piece is this linear operator T on a vector space V needs to be self-adjoint, or T is equal to its adjoint, and we need the inner product of T operating on any arbitrary vector V in the vector space with the vector V is non-negative. That's what we mean by a positive operator. It has these two parts. It's self-adjoint, and this inner product of TV with V gives us a non-negative value. Here is all of those statements that are equivalent that's captured in Theorem 27 of Chapter 7. If we're given a linear operator T, then the following 5 statements are actually equivalent. And we'll prove this in a little bit, but let's just remind ourselves, and I've tried to alternate colors so that they stand out. T is a positive matrix, T is a positive operator, which means that it's self-adjoint and it has this non-negative inner product relationship. Is equivalent to T is self-adjoint, obviously, since that's included in part of the positive piece, and this is different. All of the eigenvalues of this linear operator are non-negative. T, the linear operator, has a unique positive square root. That's if it's positive. T, D, has a unique self-adjoint square root. That directly follows from C, since a positive square root, part 1/2 of that says that it has to be self-adjoint. So if we have a square root that's positive, by definition it's self-adjoint. And it also satisfies that second property if it's positive. So D is just sort of 1/2 of the two pieces of having that positive square root. And finally, the last, or the 5th statement that's equivalent to T being positive and all the others is there exists an operator S that's a linear operator on this vector space such that we can split the positive operator T into S adjoint operating on S. So that's just a restatement of what we talked about last time, and we'll prove that in a little bit. But before we prove that, let's just remind ourselves of what square roots we looked at, or some of the square roots that we looked at. T1 gives rise to a couple of square roots, plus or minus 1 in the 1, 1 entry. T2 has a square root S sub 2 that has a little bit more information in it than what T1 and S1 looked like. T sub 5 We looked at T sub 5 actually having either the positive signed square root or the blue signed square roots for a factoring of this matrix T sub 5. Let's now look at some of these matrices Q and whether or not they're positive. So we just looked at some square roots. Let's now look at some matrices and try to determine if they are not positive. First, let's say we start with Q1 equaling 1, 0, 0, 2, and we would expect that to be positive. Remember the definition of a matrix being positive. If Q1 is positive, then it's self-adjoint, and this one is. Which it's a matrix, so now we look at its complex conjugate transpose, and in fact the diagonal is real, so that sort of saves us. And we really want to look at whether or not the inner product is true or relationship. But even if we looked at here what we've now stated for theorem 727, if we just looked at the eigenvalues of Q1, those are right on the diagonal since it's a diagonal matrix, and those are both positive. So these two combined give us statement B, that T is self-adjoint, and so if it's a matrix, the matrix representation is self-adjoint and all eigenvalues are non-negative. Statement B of theorem 727 is addressed by what I've indicated in these two blue lines, and that then is equivalent to statement A, and statement A says that Q1 is positive. So that's one way of verifying that Q1 is positive, but now let's look at it in terms of the definition of a operator being positive. We need it to be self-adjoint, which it is, and we also need it to sort of satisfy this second, or we do need it to satisfy this inner product relationship. We need this to now be non-negative for every vector v in our vector space. If we now look at Q1 times a vector v, this is 1, 0, 0, 2 times v1, v2, inner product with v1, v2. If we now use Q1 to essentially scale the v1 vector, it now becomes v1 and 2v2, which is going to be then inner product with the vector v. And this now says do component-wise products. That gives us then v sub 1 squared plus 2 times v sub 2 squared, and no matter what v sub 1 and v sub 2 are equal to, or for all v1 and v2, this is going to give us a non-negative answer for all v in R2. Because Q1 was self-adjoint, that was the first piece. That's sort of this piece. And the second piece was this inner product is non-negative. Then we can conclude from the definition that Q1 is in fact positive. And this piece right here is sort of the interesting piece. This one now is telling us that it is non-negative, that inner product, with that particular matrix Q1. Let's look at another matrix example of whether or not a matrix is positive. Let's say 2 is now Q sub 2. Let's do it a little bit more than just diagonal. Let's say that it's now 2 minus 1 minus 1, 4. Q2 is self-adjoint. It equals its transpose. Now let's see if it satisfies the second property of a matrix or an operator, in this case in the form of a matrix, is in fact, this inner product is non-negative. So that now we are going to take Q sub 2 and use that to scale V, and Q sub 2 in this case is the matrix that we've just identified, and we will allow V sub 1, V sub 2 to be the two components of our arbitrary vector V. This now, if we use Q1 to scale V, we end up with 2V1 minus V2 in the first component, and minus V1 plus 4 V sub 2 in the second component. That vector now needs to be inner product with the vector V. Again, if we do this component-wise product, we have the first components multiplied and added to the second components multiplied. We end up with 2V1 squared minus V1 V2 minus V1 V2 plus 4 V sub 2 squared. This is actually, 2's are common to all of those terms if we combine the middle two. So if we factor out the 2, we have V1 squared minus V1 V2 plus 2 V sub 2 squared. But we can create that minus V1 V2 if we completed the square. We now have V1 minus 1/2 V2 squared, but that means that we've added in 1/4 V sub 2 squared, so let's now subtract off 1/4 V sub 2 squared plus 2 V sub 2 squared. So we just completed the square, and now we can combine those V sub 2 squared terms and end up with V1 minus 1/2 V sub 2 squared plus 1/4 less than 2, or that's now 7/4 V sub 2 squared. Each of those terms involving the variables in the square brackets can only be non-negative, so in fact we do satisfy that second condition on a matrix being positive, which is the inner product condition, so that Q sub 2 is positive. Meaning this particular matrix leads to this kind of a quadratic form, and that quadratic form is going to be non-negative for all values of V, V1 and V2 being the coordinates. Let's look at another example. Let's say this is example 3, so we'll call it Q sub 3, and let's now make that 2, 4 on the diagonal, but on the off diagonal let's give it minus 4, minus 4. This now looks a little bit different than that one, meaning the off diagonals have a little bit more negative value, but Q sub 3 is self-adjoint, so we've now satisfied the first condition of Q sub 3 being positive. So let me just say that this is self-adjoint. It equals its transpose. And now we want to check the second condition, which is Q sub for any vector V. So if we now look at Q sub 3 inner product, or Q sub 3V inner product with V, we now have 2 minus 4 minus 4, 4 V1 V2 inner product with V1 V2. Or this is now 2V1 minus 4V2 and minus 4V1 plus 4V2 we need to form the inner product of that vector with v1, v2. Again, taking this component-wise multiplication, so that we now have 2v1 squared minus 4v1 v2 minus 4v1 v2 plus 4v sub 2 squared. Again, we can factor at least a 2 out. We have v sub 1 squared minus 4v1 v2 plus 2v sub 2 squared. Now we can try to complete the square. We can say, oh, we have v1 minus 2v sub 2 squared. That will give us the first two terms, but it gives us an additional term of plus 4v sub 2 squared, so we have to subtract 4v sub 2 squared plus 2v sub 2 squared. And now we end up with a different looking behavior on this quadratic form. We now have v1 minus 2v sub 2 squared minus 2v sub 2 squared. And that we can't determine a sign that it will consistently be, so this particular expression is not determined, but it's indeterminate. Meaning we could actually find different v's that will produce a different sign on that inner product. If you look at the result of this expression, this quadratic form, when v is 1, 1, then you'll find that that inner product becomes negative. If you looked at a different v, you can find a v where it becomes positive, meaning it depends on what v is, what the sign of that inner product expression will yield. You can also look at the eigenvalues of q sub 3, and those are actually, one is negative, minus 1.123, and the other one is 7.123, so that's another way of showing that it's q sub 3 is definitely not positive, or this lack of being able to show that the inner product was always non-negative for no matter what v we picked. Those then show that q sub 3 is not positive. Those are some examples then of what a matrix might look like relative to whether it is positive or not. So with that sort of insight or additional information, let's now return to, now that we have a little bit better feel for what a matrix might have to look like if it's positive, let's go back to this theorem 727, and now for these linear operators t, if it's positive, that means it's also equivalent to these other four statements. Let's now show or prove that in fact A implies B, B implies C, C implies D, D implies E, and if we then can show that E implies A, then we have all of these statements being equivalent to each other. Let's now make that happen. So let's look at a proof of theorem 727, and as I just mentioned, we'll do this by showing that statement A is going to imply B, B is going to imply C, C is going to imply D. We've already mentioned that. D is going to imply E, and then E we can show goes back, and we can find our tail so that now E implies A. Let's now look at the first implication, or that statement A can be shown equivalent to statement B. Statement A was that the linear operator the linear operator T was positive. Statement A says that the linear operator T is positive. And remember what that says. That says that we have two conditions for T to be positive. One is this operator T needs to be self-adjoint, and the inner product of TV with V is non-negative for all V in the vector space. And what was statement B? Statement B said that T is self-adjoint, so that's already met when T is positive. We're assuming A is true. So now A being true says that T is self-adjoint and that inner product expression is true. So the first part of B is automatically shown from the first condition on T being positive. Now let's see if we can find if the eigenvalues are non-negative of this operator. If that's the case, then let's select an eigenvector. Let's let V be an eigenvector. If V is an eigenvector, then TV with V is equivalent to lambda V, but we already know, since T is positive, that TV, the left-hand inner product, is greater than or equal to 0. Therefore, we have lambda, when we factor it out, in terms of the homogeneity of the first slot, we now have lambda VV greater than or equal to 0. We know that the inner product of V with itself is the norm of V squared. That's always non-negative, which now says that lambda is greater than or equal to 0, or that lambda is non-negative. So now we've shown that, in fact, statement A implied B. Now that we have statement B, let's show that B implies C. B was, again, it's self-adjoint, and all the eigenvalues are non-negative. Let's see now if T has a unique positive square root. Or let's just say a square root. So now we're given that T is self-adjoint. If it's self-adjoint, then we know from the spectral theorem that we can find orthonormal basis vectors, and let's just call those E1 through E sub n, or the eigenvectors of this self-adjoint operator, form an orthonormal basis. That's from the spectral theorem. And we're told from statement B that all these eigenvalues of the operator are non-negative. So now that we have that, suppose we let, or in other words, define a new operator. Let's create an operator S, from this condition. Let's say that S e to the j, where e to the j is the jth orthonormal basis vector. And now we know that all of the lambdas are positive, so let's take the jth eigenvalue, and since it's non-negative, we can take the positive square root of that. And let's say that S will be created such that S e sub j is the square root of lambda sub j e sub j. And let's do that for all j, where j ranges over all n orthonormal basis vectors. So that's what we are creating, or we're defining S to be that particular, satisfy that condition. If we actually look at that, or look at what that produces, we can actually use that relationship to construct a square root. That's what S is going to turn out to be. So here is an aside on constructing S. Suppose now that we have S that satisfies this S e to the j square root of lambda j e to the j for all j. Then we can take S and pack all of those e's into a matrix, a square matrix that's containing all those n orthonormal basis vectors e1 through e sub n. But that's just scaled orthonormal vectors e1, e2, e sub n, where they are scaled by the square root of lambda 1, square root of lambda 2, square root of lambda sub n. So those are on the diagonal of a diagonal matrix. If we were to now call this matrix E and this matrix E, now do you see that in fact we can create S by taking E, and we have this diagonal matrix made up of the positive square roots of these eigenvalues of the original operator. And if we post multiply both sides of this blue formula by the inverse of E, then we have our square root S, where the square root of our linear operator T is in fact S. So that was just an aside on how we could actually construct such a square root from an operator S satisfying this black relationship. Also from that relationship, S e to the j equaling square root of lambda sub j e to the j. Suppose we operate on the left with S, so that now we say, oh, S times S e to the j is going to equal S times the square root of lambda sub j e sub j. But the square root of lambda sub j is a scalar, so that can be slid to the left of S, so that now we have the square root of lambda sub j times S e to the j. But now S e to the j, by definition, is the square root of lambda sub j e to the j. So now we have the square root of lambda sub j times the square root of lambda sub j. That just gives us lambda sub j times e to the j. But what do we have right here? Well, right there we have S squared. E to the j is now equal to lambda to the j, e to the j. But what was equal to lambda sub j e to the j? That was just t e to the j for all j. And now if we simply look at the leftmost expression and the rightmost expression in that equation, we can see then that t is equal to s squared, or s is in fact a square root of this linear operator t. So now we are trying to go from B to C, and now we've shown that we can find a square root. We want to know, is this S that we've built, is it actually positive? We found a square root for this linear operator t, where the t now is such that we've satisfied statement B, and statement B was that the linear operator was self-adjoint and all of its eigenvalues were non-negative. Now we need to see if S is positive. So for something to be positive, we need it to be self-adjoint and to satisfy that inner product condition. So first, let's show that S is self-adjoint. Remember what we had defined S to be. S is this E, and let's just call that diagonal matrix of positive square roots. Let's say a matrix lambda to the 1/2, so that now S is equal to E lambda to the 1/2. That's a diagonal matrix with lambdas square rooted on the diagonal times e to the minus 1. But remember what E was. E was this orthonormal or unitary matrix. E inverse is actually equal to the complex conjugate transpose of E, since the matrix E was made up of these orthonormal basis vectors, which are possibly complex, which is why we're saying complex conjugate transpose. Now, we need to show that S is self-adjoint, so if we find in the matrix representation of this, if we could find that it was equal to its complex conjugate transpose, then it's self-adjoint. Let's then find or compute the complex conjugate transpose of S, where S is now E lambda to the minus, or E to the 1/2 e to the minus 1. So let's now conjugate that. We now have E conjugate lambda to the 1/2 conjugate e to the minus 1 conjugate transposed. It doesn't matter if I transpose and conjugate or conjugate and transpose. Now if I transpose that, I now have e to the minus 1 conjugate transpose. The conjugate of this real square root expression doesn't matter, and the transpose of a diagonal gives us back the diagonal, but let's go ahead and keep that in play for now. And then we transpose the conjugate, or the first term in that expression. But E inverse is really just the conjugate transpose, so we conjugate transpose that back and we end up with E. As I said, the diagonal when transposed gives us back the diagonal, so that's now E to the 1, or lambda to the 1/2, and E conjugate transpose is just E inverse And that's what we started with for our definition of S. So in fact, the complex conjugate transpose of S is equal to S, so that this square root that we've created is in fact self-adjoint. We also need to show that it satisfies this inner product non-negative result. So let's just say we can also show that the inner product of the square root S that we've created operating on V, inner product with V, is in fact equal to this sum over J of the magnitude of A sub J squared, square root of lambda sub J, and that was the positive square root, and the absolute value of A sub J is obviously non-negative, and that sum then is non-negative. So we want to show that is true. Here are the steps. Suppose, since we have V as an arbitrary vector and E as an orthonormal basis, we can write V as some linear combination of those orthonormal bases. Let's just say it's A1E1 plus A2E2 plus A sub n E sub n. Then if we operate on V with S, now we have A1 through AN are just scalars, so let's factor those to the left of the operator S, and we have A1 SE1 plus A sub 2 SE sub 2 plus A sub n S E sub n. But all these E's, these orthonormal basis vectors, were in fact eigenvalues of S, so that now we have A1 where they were the positive square root of the original eigenvalues of T. So this is the positive square root of lambda 1 E1 plus A2 positive square root of lambda sub 2 E2 plus A sub n positive square root of lambda sub n e to the n. If we now look at that expression for SV, inner product with V, I hope you can see that we now have A1 times its conjugate, so that now just gives us the magnitude of A1 squared times the square root of lambda 1, and these E's are orthonormal, so we only have these really component pieces from the coefficients of E1, E2, etc. So that now we have A sub 2 magnitude inner product, or magnitude squared times square root of lambda sub 2, etc., up to A sub n's magnitude squared square root of lambda sub n. And that is greater than or equal to 0. Thus, if we started with statement B, we've now shown statement C, that we do have a positive square root of that linear operator. Now, C implies D by definition, because C said that we had a positive square root, and now we're saying that we have a self-adjoint square root. Well, half of something being positive is that it's self-adjoint, so positive implies self-adjoint by definition. So we've now concluded that C does imply D. D now says that we have a self-adjoint square root, and we want to now use that to see if D can be shown to be equivalent to E, or if D does imply E. So S from statement D is self-adjoint. And we know from earlier that S squared is equal to T, that it's a square root of the linear operator T. Therefore, if we have T, that's S squared, because S was a square root of T. So we can rewrite S squared as S times S, but S was self-adjoint. If it's self-adjoint, we can just replace S with S adjoint, and now we've parameterized or factored our linear operator T as S dagger, or the adjoint of S times S. So now we have been able to conclude that D does imply E. What we now are left with is trying to complete the circle, which says let's now see if we can show that E does imply A. E says that we can start with our linear operator T is factorable in terms of S dagger S. So now if we look at T dagger, or the adjoint of T, if we start with S dagger S and take its adjoint, now again we have to remember how to take the adjoint of a product. We now take the right term in that product, and that now becomes the left term adjointed, and we now have S adjoint adjoint, or we now end up with S adjoint S, but T was S dagger S, and now we've shown that T dagger is S dagger S, so that T is equal to T dagger. And now we've shown that at least the first half of this linear operator T being positive is true, because T is now self-adjoint. We now need to see if this inner product of TV with V is in fact non-negative. But again, statement E says that T can be factored as S dagger SV, or T can be factored as S dagger S. So now we have the inner product written in terms of S dagger S. We can slide that S dagger into the second slot by taking its adjoint, so that we now have SV, and we have S dagger dagger times V. But if we take the adjoint of the adjoint, that gives us back S. And now we have an inner product of a vector with itself, which we know by the positivity of the inner product that that's greater than or equal to 0. Thus, we've just shown then that E does imply A, because now we've shown the two pieces, or the two halves, of this linear operator T being positive. It needed to be self-adjoint, and it needed to satisfy this inner product relationship, so that we've now shown that E does imply A. That concludes then theorem 720, or the proof of theorem 727, or the equivalence of these 5 statements dealing with positive matrices. Recall that the square root of lambda, by definition, denotes the unique non-negative square root of a non-negative eigenvalue lambda. And what we are going to state now, or see, is that that now can be generalized, or that generalizes, and we'll use that in our notation. If we now say the square root of this linear operator t, we are going to say that that defines the unique positive square root of this operator t. That's our notation. When we write the square root of this linear operator t, we're meaning that that's the unique positive square root of t. That now allows us to get to proposition 28 in chapter 7, and that is that every positive operator on our vector space V has a unique positive square root. Remember, these positive operators are pretty, what do I want to say, specific. And so if we have a positive operator, then we can find a unique positive square root for that. And that is really coming to us from, or by construction, that we performed when we were showing that B in fact implies statement C in the proof of theorem 727. That shows it's possible, and what I would defer you to is the textbook for the proof of proposition 28. Let's now look at an example of that in the form of a matrix. This example is going to then find or compute the square root of a positive matrix. And the positive matrix that we'll use is Q sub 2 that we looked at the very beginning of this particular session. Q sub 2, as a reminder, is this 2 minus 1 minus 1, 4. And we know from before that that is a positive matrix. We can show that it does have this quadratic form that's always non-negative. So that's positive from before. We could find the eigenvalues of that. So let's just say that the eigenvalues of q sub 2 are 1.58579. I'm using quite a few significant figures. And 4.41421, where I'm going to call this smaller eigenvalue lambda sub 1 and this larger eigenvalue lambda sub 2. And for those eigenvalues, we can, in fact, find their corresponding eigenvectors. So that now let's say that x, which is made up of E1 and E2, E1 is now minus 0.92388, sitting on top of minus 0.382683. This is now the orthonormal vector E sub 1, and E sub 2 is in fact positive 0.382683 and minus 0.92388. E1 and E2 form an orthonormal basis of this two-dimensional vector space. And if we look at what happens when we take x times its transpose, we get the 2 by 2 identity matrix. What we're trying to do is find a square root of q sub 2, and remember how we had suggested we might be able to do that. Suppose we now have the square root, let's call it s sub q. We build it up. We take s sub q. We don't know what that is yet, but we say that when it operates on E1, that's going to give us the square root of lambda sub 1 E1. And when s sub q operates on E sub 2, it's going to give us the positive square root of lambda sub 2 scaling E sub 2. If we combine those two into one matrix structure, we now have S sub q times this matrix, E1, E2. Then we have E1, E2. So this is now our matrix X. This is our matrix X, and on the far right-hand side is the scaling of those orthonormal vectors, which are possible or is made possible by forming this diagonal matrix with the square root of lambdas on the diagonal. We have X, capital X, and we have these square root of these eigenvalues we can compute. Remember that the inverse of x is just its transpose, so s sub q is now this x times the square root of lambda 1, square root of lambda sub 2 on the diagonal, times x inverse, but this x inverse, remember, because it's orthonormal, is just x transpose. And this now, if you form that matrix product, you end up with 1.3825 and minus 0.297593 minus 0.297593 and 1.97774. And in fact, now we have created this square root of q sub 2, if you were to combine s sub q with itself or multiply that together, you would end up with the original positive matrix q sub 2 as an answer. So now we have constructed a way to find a square root of a positive matrix. We find the eigenvalues and eigenvectors and use those with this relationship on or defining the S. We can now use that to build our square root matrix. So that now if we have a positive matrix, we can find a positive square root of that positive matrix, and that's going to allow us to perform scaling operations. Let's now move into the other sort of piece of what we can start looking at in terms of scaling and rotations. Now let's look at isometries, which in the second edition, this is coming to us on page 147. Let's define this like we've defined positive matrices or positive operators. An operator S, it's a linear operator on this vector space V, is an isometry if we were to look at the norm of S operating on a vector V. That norm is the same as the norm of that vector V, and that's true for all vectors V in our vector space capital V. If we have an operator S that satisfies this norm condition, then we call that an isometry. Let's just make some notes. One is that this isometry operator preserves the norm, or we could say it's norm preserving. We don't change, we don't scale, we don't influence the norm of a vector by operating on it by S. And this isometry S is a generalized rotation. If we wanted to think of one of the simplest isometries, then let's think of a one-by-one matrix or a scalar. And now if you want to think of what is an isometry generalizing, you can think of isometries as a generalization of 1 or minus 1. So now we're reflecting if it's minus 1 and we're not doing anything with it being 1. Let's look at an example of what this might mean. Suppose we let S be a linear operator, and let's now give it eigenvectors that form an orthonormal basis on the vector space V. So now let's let S be a linear operator with S E sub j equal to lambda sub j E sub j for some orthonormal basis E1, E2, E sub n on the vector space V. So now we're saying that S has this eigenvalue-eigenvector relationship where the E's are an orthonormal basis. If we impose this norm constraint or norm preserving property on this operator S, does that in fact force some particular relationship on these eigenvalues lambda sub j? Does it enforce some kind of structure? Let's now see what happens when we force the norm of SV to in fact equal the norm of V. So let's see what happens. Let's write V in terms of this orthonormal basis, and let's then see what happens if S has eigenvectors made up of this orthonormal basis, and see what happens when we equate the norms of these two. What does that force on the eigenvalues? So now for V, a vector in this vector space V, we can write it, or we can decompose it as V is this inner product of V with E1, scaling E1. The inner product of V with E2 we can use to scale E2, so that we can now decompose any vector V in this vector space along or in terms of this orthonormal basis. Now, using a result from before, we know that the square of the norm of V, remember E1 through En are orthonormal basis vectors, and the inner product of V with Ej is just a scalar. So we can now take the magnitude, or the absolute value, of each of these scalars and square their absolute value, and that will produce the square of the norm of V. That's coming to us from before. That's now what V squared, or the norm of V squared, is. Let's now look at what happens, or what we have, if we look at the norm of SV. SV, again, we've now decomposed V in terms of this inner product of V with all the orthonormal basis vectors E's. Those inner products are just scalars, so we can now have the inner product of VE1 slid out in front of SE1. VE sub 2's inner product is now going to scale SE sub 2, and we just keep going. So that VE sub n is going to scale SE sub n. But remember how we defined lambdas. We said that we now have this orthonormal basis E sub 1 through E sub n that are forming the eigenvectors of S, and the associated eigenvalues were lambda sub j. Anywhere we have S E sub j, that gets replaced with lambda E sub j, again where lambda is a scalar, so that now we can say that that's lambda 1 V E1 inner product times E1 plus lambda sub 2 V E sub 2 inner product with E sub 2 and lambda sub n V E sub n inner product with E sub n. Now if we look at the norm squared of SV, remember lambda 1 and this inner product, or the lambda sub j's, and the inner product of v e sub j, those are both scalars, and we're forming this norm squared. Well, all we have to do is take the scale, or the scalar, and take its absolute value and square it. In this case, the scalar is made up of two pieces. And if we now see that this right-hand side needs to equal this right-hand side, that now forces some condition on these absolute values of these eigenvalues. With SV squared equal to the norm of the vector squared, then in fact that says that the magnitude of all of these lambda sub j's squared has to equal 1 for all j. And now that tells us something about this isometry. These isometries now have all of their eigenvalues having a magnitude of 1. And that's an important result. So if S is an isometry, then we can also see that S is in fact injective, because the only time that SV is going to equal 0, that can only be true for V equal to 0, because of this particular way that we have decomposed V, any vector V, can only be true for V equal to 0 if the norm of SV is equal to the norm of V. And because of that, since it's injective, it's now one-to-one. S is a one-to-one mapping, or allows for a one-to-one mapping. It has a trivial null space, which says then that every isometry is invertible. So the only way that we can have SV equal to 0, if this S is an isometry, so it preserves the norm, then if that's 0, the only way that the norm of V is 0 is for V to be 0. So we have V being the trivial vector, or the 0 vector, and that says we have a trivial null space, and so we have our isometry. Any isometry is injective. If it's injective and it's square, it's now invertible, and so now we can make that particular claim. Like we had for Theorem 727, we can actually create a long list of equivalent statements for isometries. And that's theorem 36 in chapter 7. Let's say we're now given this linear operator S on a vector space V. Then that allows us to say or conclude that the following statements are equivalent. Just like we had a lot of equivalent statements for a positive matrix, now we have a lot of equivalent statements if we have a matrix that's an isometry. So let's say that the first statement A is that S is an isometry. That's equivalent to statement B, which says that if we take the inner product of SU with SV, that's the same as the inner product of U with V. And that's true for all vectors U and V in our vector space V. So it has this nice inner product consistency, or it doesn't do any scaling of the inner product if S is an isometry. Another equivalent statement is that S adjoint times S, or operated on S, is actually the identity map. So you can get back to where you started if you operate on a vector with S, an isometry, and then its adjoint. You basically end up where you started. It's the identity map. If you now have SE1, SE2, SE sub n, that collection of vectors is orthonormal whenever E1, E2, E sub n is a list that's an orthonormal list. Another equivalent statement is E, and that is that there exists an orthonormal basis E1, E2 up to E sub n such that SE1, SE2, SE sub n is orthonormal. In that theorem 736, it continues with more statements, and those are F through J, which I'm not going to repeat, but it's basically the same as A through E that we just looked at or stated. It's just we can make statements F through J the same, except now we need to replace everywhere we had S, we need to substitute its adjoint. So that this isometry S that we started with and its adjoint are effectively interchanged to produce statements F through J that are equivalent. So if we try to summarize that, and I'm going to just say see Axler for the proof. And to summarize that theorem, we can make some comments or some remarks. If S is an isometry, its adjoint is an isometry. So S is an isometry if and only if its adjoint is an isometry. S adjoint can be thought of or is equivalent to the inverse of this isometry, and that we could see from statement C above. If we look at S and its adjoint, they in fact preserve inner products. And that's if we look at statement B and statement G. S and its adjoint preserve orthonormality. There we can see that that's true for D and I. And let's just make one more note. Since S dagger S is equal to the identity, that's also equal to S dagger. This is true from statement C. This is true from its counterpart, which is statement H. Well, if the left is equal to the identity, which is equal to the right, then the left and the right are equal. And if we have those equal, then we have S dagger S is equal to S dagger, or S and its adjoint commute so that all isometries are normal. And that's what we just had up here. S, let's say, commutes with its adjoint S dagger. And we'll stop at that point.